In this video, we're going to be rewriting expressions using exponent properties. Now, I'm going to be going through it. Try not to skip any rewrites, but oftentimes with exponent properties, you'll see people kind of jump through and skip steps. It's very common with exponent properties. But for this first one, for a over here, we have 81 to the 5 to 6 times 81 to the negative 1/3. Well, when we are multiplying two expressions with exponents, if those expressions are the same base, then the exponents properties say that we can add the exponents. It's the product of powers property. So according to the property, we add the exponents. However, we do need a common denominator to actually add these exponents. I think the common denominator would be 6. So we would have to multiply the second fraction by 2 over 2. Making it 81 to the 5/6 times 81 to the negative 2/6. And if we add the exponents now, we get 81 to the 3 over 6. 3 over 6 reduces to 81 to the 1/2. Now, in some cases, you may be able to simplify this farther, especially if it is a number like it is here. 81, I know, is a perfect square, and I know this radical, or this fraction, corresponds to a radical with a root, or index, of 2. See, it's the second root of 81 to the first power. The square root of 81 is 9, and then 9 to the first power is just 9. So overall, this first expression simplifies into 9. Now for the second expression, b here, we're going to start inside the parentheses and see if we can combine anything inside. I see that there's an x on top and an x on the bottom. When you have variables connected by division, according to exponent properties, you want to subtract the exponents. So the exponent on top is 1. 1 minus 1/2 is 1/2. So x to the 1/2 times y to the third, to the 2/3. The next property is that we're going to use, since we can't combine anything else in the parentheses, is we'll use the power, let's see, the power, I forgot all the names. I don't use the names too often. The product of powers, that's the one we have to use next, because we have multiple things connected by multiplication on the inside of the parentheses. So we're going to distribute that exponent on the outside to each of the things inside. Remember that this property does not work if there's addition or subtraction inside the parentheses. But we will essentially distribute this exponent to both factors inside. So it'll be x to the 1/2 raised to the 2/3 times y to the third raised to the 2/3. And then we have to use the power of power properties, which says that if we have a power raised to a power, we multiply the exponents. So 1/2 times 2/3 would be 2/6, which reduces to x to the 1/3. And then when you do the second one there, 3 as a fraction is 3 over 1. So you multiply the tops, giving us y to the 6 over 1 times 3 is 3, which reduces y to the second. So overall, this will be the simplified expression. And I can't go farther and turn it into just a single thing like I could with the other one, just because x isn't a perfect power. Okay, so in this example, we're going to simplify the expression, the cube root of 54x to the 10th. Now, we've done similar things earlier in the year, whenever it was the square root of 24, simplifying radicals for quadratic equations and such. But we're going to do the same approach here. We need to ask ourselves, first of all, is 54 a perfect square? we're going to focus on that number first. If 54, I said perfect square, but I mean perfect cube because we have an index of 3. But if 54 is a perfect cube, then we don't have to break it down farther. So I'm just going to take a peek at my quick reference chart here. We have the cube column, and as you can see, 54 is not anywhere on this list. It goes to 64, so 54 would be somewhere in here. Now we want to ask ourselves, since 54 is not a perfect cube, is there a perfect cube that goes into 64 evenly? So if we try them, you can find out that 27 goes into 54 evenly. 54 is 27 times 2. Now we're going to also do the same thing with the x to the power of 10. So if you recall from previous lessons, the way we dealt with the variables is we turned it into a fractional exponent. So it was exponent over index. So does our index of 3 go into our exponent 10 evenly? Well, unfortunately, it does not. So there's a number of ways we could handle this. And for now, just to emphasize the properties, I'm going to handle it this way. I'm going to look for a number that's smaller than 10 that 3 can go into. So 10, 3 doesn't go into 10, so let's go a little bit smaller. What about 9? Does 3 go into 9? Well, yes, 3 does go into 9. 9 divided by 3 is a whole number. So I'm going to split the x to the 10th up into x to the 9th. But we can't just change the exponent just because we want it or need it to be this way. We have to keep things balanced out. The same thing we did with the 2. We had that extra factor. Well, just like with the numbers, we have an extra factor here. We have an extra factor of just x to the first. When you multiply variables, you add their exponents. So 9 plus 1 makes 10, which means we haven't changed the total number of x's that were available in the first place. So the 2 and the x to the first are kind of my leftovers that were not part of the perfect cube. Now that we have that, we are going to separate, like we have done before, with the property for radicals that says if we have a times b in the radical, we can separate it into radical a times radical b. Applying this property, we are going to separate the cube root of 27, and we're going to separate the cube root of 9, x to the 9th. We're going to leave the stuff highlighted in pink, the stuff that was not part of our perfect cubes, inside the radical. And then we'll just go ahead and simplify each of the ones that were perfect cubes. The cube root of 27 was just 3. And as an intermediate step for x to the 9th, we would rewrite it as x to the 9 over 3, which simplifies into x to the 3rd. And then the stuff that was not part of the perfect cubes, this leftover, just kind of comes down for the ride. So the cube root of 2x to the first, which is just 2x. And there we have it. And if I want to write it a little bit nicer because that spacing's kind of bad, 3x to the 3rd cube roots of 2x. Just as a little bit prettier of a way of writing it because my spacing between the 3 and x is pretty drastic.